started. First thing we're going to look at is finishing off some section 8.3, the applications. What we're essentially going to do is calculate what's called hydrostatic force. And there are two versions of the formula that you're going to use, and they're kind of cryptic, but that's why I'm going to do them. The first one is 62.5 times this integral, and the second one is 9.8 times 10 to the power of 3, that integral. And the reason you need these special magic numbers is that when you do feet in pounds, 62.5 gets used when you do hydrostatic forces. On the other hand, when you use meters and kilograms, use 9.8 times 10 to the 3. 62.5 does have a meaning. It's how much 1 cubic foot of water weighs. And this fella, well, can you guess where the 9.8 comes from?
Is that gravity?
Yeah. And the times 10 to the 3 is essentially kilograms. So there's 9,800 kilograms in a cubic meter. So yeah, it's just magic. You need these numbers. Now, what exactly is hydrostatic force? Well, I want you to, I'll get that formula to the side. Essentially, there's only 4 questions you're going to do. I think it's 4 or 5. So here's the first one. What you have is some water and a plate. And the plate's either going to be rectangle, as this one is, or it's going to be triangular. So this is a bit like question 11. And imagine you've got this plate, and it's 4 feet in that dimension. And in this dimension here, it is 7 feet. And it's 2 feet under the surface. So what's going to happen here is that you are going to calculate the total force on this piece of metal. And it's quite important to be able to calculate what are hydrostatic forces because, well, you can imagine a submarine or just the part of a ship that's underwater. It's quite important that you can calculate how much force is being applied on that, you know, to tell if it's going to be strong enough to take it. I mean, you wouldn't want to take a submarine down and then find out at 20 feet it was going to crush and die. That would probably be a bad finish to your day. So we need to calculate these things. So how are we going to do it is the key, and how does this formula work? Well, the first thing about this formula is because it's feet, we use the top one. So the formula for getting the hydrostatic force, which is what you're going to be asked in every single one of these questions, is 62.5, the integral from a guy called A to B, depth, width, dx. So I just need to show you where to find all these bits and you are good to go. So what you do is you take a horizontal strip at a random position, this strip here, and I count the distance from the top of this plate to that guy, and I'm going to call that distance X. Now, there are 2 things you need, a guy called depth and a second guy called width. Let's find depth. When I write depth, what I really mean is, what is the distance from the top of the water to that strip? Now, from the top of the shape to the strip is X, and from the top to here is another 2. So are we okay with that being X add 2? Are you comfortable how I figured out what the depth of that strip is? It's 2 feet plus another X. Okay, I got a thumbs up on that. Now, the second thing is called the width. And the width we're talking about here is the width of that green strip. Well, in this case, isn't the width the same, no matter if you're at the top of the rectangle or the bottom? Isn't it always 7 feet? So we're already filling in quite a lot of the missing pieces. The depth is x add 2. The width is 7. Now we have these guys A to B. A is what's the starting value of x for this shape, and B is the finish. So if you imagine x being 0, wouldn't that take you to the top of the plate? And when x is 4, wouldn't that take you to the bottom of the plate? Are you comfortable about how I got 0 to 4? Where that came from? Right. That's pretty much it. The hard part of the question is done, right? I would probably just leave that 62.5 exactly where it is. Depends on how you want to tackle the next bit. I would probably just distribute the 7. And then that would allow me to do 7 over 2x squared plus 14x, right? Antiderivative, power rule. And just evaluate it at 0 and at 4. And what's that going to get me? It's going to get me 7 over 2 times 4 squared plus 14 lots of 4. Take away a whole load of nothings. And probably at this point here, I think the calculator should take over. So let's just clear that out of the way. So I'm going to go 62.5 times, put a bracket, I don't know, 7 divided by 2 times 4 squared, which I know is 16, plus 14 times 4, close the brackets, and I get 7,000. So the hydrostatic force, the total force on that one piece of metal is 7,000 pounds. So far, so good? Right. Suppose I took that plate and made it 20 feet under the ground. Right, under the water, I mean, right? So instead of here, it's way down here. Wouldn't the depth turn into x plus 20? But wouldn't everything else stay the same? That makes sense, because when I do these limits, I'm talking about the top of the shape, x is 0, to the bottom part of the shape, x is 4, because there's 4 feet. And so you can do a plate at 50 feet deep, 500 feet deep, any number you like. Like, I don't know if you've watched programs, but have you ever seen programs where they do things really, really deep under the water? Do you know that the water pressure, that's all hydrostatic force is, right? The water pressure is extreme, right? The kind of the you know, submarines and a few things can go down really deep, but they're built in such a way that they are built to, you know, take that kind of force. That's a lot of force, isn't it? 7 pounds, 7,000 pounds on what, 28 square feet. You can imagine doing a quick division. Each square foot of that has got a fair amount of force pushing on it. And that is one question done. I'm only going to do 3. So that's the simplest shape, a rectangle under the water. Okay. Well, before I move on, can you pretend this question was exactly the same with one change? 2 meters, 4 meters, 7 meters, right? So the units were meters and not feet. What would be the only change to my calculation?
$9.8 times 10 cubed instead of 62.
Yeah, exactly. That's it. Now, if we weren't in America, do you know that formula would never even been taught to you? They would only had a single formula. But, you know, we don't not live in America. There's a double negative for you. So we have to apply it to that question. So this is the second example, and this one is like question 12. And they've got it written down and they've actually got a picture, but the picture doesn't have all the information on it. So I'm going to draw my version of their picture. And you've got a right angle triangle, looks like that. And it is, let's see, triangle height of 6 feet and a base of 8. So from there to there is 6 feet. And from here to here is 8 feet. And it's 4 feet, at least the top piece, is 4 feet under the surface. So the hydrostatic force is another 62.5 again. The integral from A to B, the depth times the width. This is going to be a little bit harder than the first one, which was just a rectangle. Formula's the same. It's going to go 62.5. Right, so let me put my little random strip. We'll put it here. And the distance from here to here, right, from the top of the shape to the strip, is going to be called X. Right, that nothing that different from the first question, right? Nothing weird yet. Would you, well, I was going to tell you the answer, but maybe you could tell me. The depth would be the distance, right, from the surface to the strip. So that distance there to there is the depth. What is the depth in this question?
Four plus X.
Agreed. Right. 4 to the surface plus another X. 4 plus X. So that means the depth is 4 plus X. Okay. Now, the integral from A to B represents the value of X from the top of the shape, which is always 0, at least the way I construct these, and the bottom of the shape would be 6. Are you okay from 0 to 6 as the limits of integration? You comfortable where they came from? Another thumbs up, we are good. Now, here's the sneaky part. This is what makes this a little bit more difficult. I need to find the width, right? That distance from there to there. Problem with that is, isn't the width different depending on where it is, right? It's big up here and it's small down there. So what I'm really looking for is the value for the width in terms of X. That's what I need to do. Find out what the width is, right? That green distance in terms of X. And I'm going to use a guy, which I hope you have seen somewhere in your math career. And it's called similar triangles. Some of you heard that? Similar triangles. What that basically says is, if you have two shapes that are the same shape, but one's like bigger than the other. So can you imagine this is the big right angle triangle. Now in the big right angle triangle, that's 8 feet and this is 6. And then you have a little baby triangle, right? Which is this one here. And the baby triangle, this is W. I'll call the width W, right? Be careful. What's this distance? Well, do you know that distance is 6, right? And this little piece from here to here is X. So what's that distance? How would I get it?
6 minus X.
Okay. Right, now, we've got it all set up. According to similar triangles, if you have two triangles, same shape, different sizes, the jargon is that the corresponding sides are in equal ratio. Let me show you what that means. This side corresponds to that. So 6 divided by that is the same thing as 8 divided by W. Right? Corresponding sides in equal ratio. Now, Remember what the goal here is, to find the width W in terms of X. So really what I'm going to do here is solve this equation in terms of W. So if I do a little cross multiply, 6W equals 48 take away 8X. Divide everybody by 6, so that's 8, and 8/6 is 4/3. And there is your W. So I can now go and put all the pieces together. I already got the depth, it was 4 plus X. I've just found out what the width is. It's 8 take away 4/3 X dx. Let's take it just a little bit further. So it's going to be the integral from 0 to 6. That's going to get you 32 take away 16/3 X plus 8X minus 4/3 X squared. Not a lot happening here. 32, that gets you 24/3. Well, 24 with that leaves you with positive 8/3. Now at this point, I'm going to leave the question. Wouldn't you just do the power rule, evaluate it from X equals 6 to 0, and then multiply the answer by 62.5, and you're probably going to use your calculator a lot, right? Because the numbers are horrible. And that's the end of that question. I think if you can get to there, shouldn't you be able to finish the question? Just an integral. Ugly, yes, but just an integral. So what is our third and final one that I want to do? Well, it's going to be metric, because it can be. And who cares? 4, 13, 14, 14, 13. 14. So in this case, you've got the water, and they've placed the triangle like that, a little bit different. Oops. Oh, can I change that one? I haven't started it much. I'll do 15. I just noticed 15 is much more interesting. Goes like that. You got a triangle, like something like this. And the distance from here to here is 6 meters. The distance, I guess you'd call it the height of this triangle, is 2 meters. That's good. And distance from here to here happens to be, in this case, coincidence, 6 meters. And we want to know the hydrostatic force. Well, it's going to be 9.8 times 10 to the 3, the integral from A to B of depth times width dx. There's my little guy. Okay. So from the top of the shape to here, I'm going to call that x. So the depth, which is the distance from the surface to here, right, the depth, is going to be x add 6. Are we getting kind of used to the strip is x from the top of the shape and the depth is, 6 plus x, 4 plus x, whatever it might be. So as I find these things, I guess I should put them in. That is really just 9,800, so might as well do it. Top of the shape is 0, bottom of the shape is 2. The depth is x add 6. and then we want to get the width. I'm going to do similar triangles again. So pretty much if you, unless it's right angled, I guess, but pretty much if you see a triangle, you probably want to do similar triangles. So the big guy looks like this. And I know it's not to scale, but that's 2 meters. And that's 6 meters. And the little baby triangle I'm talking about is this fella here, right, the top half. And I know that this distance here is X. And I know this distance here, well, I know it, but I'm calling it W for width. So 2 over X is 6 over W. So 2W is 6X. So W is 3X. Are we comfortable about how I got the width in terms of X using the similar triangle trick again? Which means we have this integral. So it's going to be 9,800. The integral from 0 to 2 of 3x squared plus 18x dx. I'll take it a little bit further, I think. 9,800. The integral from 0 to 2. Oops, let's not do that. I've already got that. Let's power rule it. Yeah, that's better. Evaluated at 0 to 2. So what's that? 9,800. 2 cubed plus 9 lots of 2 squared. Take away a whole load of nothings. And finish with a calculator. 9,800 multiplied by a bracket, 2 cubed plus 9 times 2 squared. And do not be surprised if you're interested, which you might or might not be, when it's metric, the force is newtons. So that's over 400,000 newtons force on a triangular plate being placed underwater. That's a lot of, what am I talking about? That's a lot of weight force. Makes you wonder how submarines actually work. Just curious, anybody in this class, because I do have submariners in other classes, anybody in this class a submariner? No. Well, now that I've shown you this number, you might not be so keen in going into the water the next time. Huge answer. Well, that is the end of section 8.3. In fact, it's the end of chapter 8. We have one more chapter, chapter 9. So let's see what we have here. We are going to be looking at differential equations. Talk about big picture before we get into the woods with these. If you're going to do engineering of any kind, you're going to do differential equations. Differential equations are very often the way in which they model physical situations. You know, the way forces would work or anything remotely to do with stresses and forces being combined in various ways. Differential equations is at the forefront. to kind of give you an idea of how big differential equations are, at Olympic College, we have differential equations 1 and differential equations 2. We have 2 full classes devoted to just one topic, differential equations. That's how big it is. Now, as some of you have already got your plan for what classes, what math classes you're going to be taking, it will not be a surprise to know that differential equations is in that list. You already know that, some of you who, if that's the pathway you're going. So we are only going to give you a taster of. You don't expect 2 weeks to cover anything in great depth. But what I want to get across is getting used to differential equations, how we talk about them, and how to solve some very simple ones. That's pretty much all we're going to do. So let's start with a very simple definition. A differential equation. Oh, from now on, nobody ever writes down differential equation. We just call them DEs, right? So a differential equation, just say DE. So for a differential equation is any equation that contains here's a shocker for you, a derivative. So you can imagine there must be like unlimited number of equations you could just create off the top of your head. But what typically happens is that these differential equations get formed from theories like the rate of change of this is proportionate to something else. And what that does is it generates a differential equation. Heat equations are just differential equations. Laplace's equations, all number of different things end up being differential. So that's all it is. So let's show you examples. You could get dy by dx equals x squared plus 4. That is an example of a differential equation. You can have it written as y dashed sine x plus 1. That's an example of a differential equation. You can have, but it's less common, f dashed x is e to the x plus x minus 1. They are all examples of very simple, but examples of differential equations. These differential equations are all called first order. Differential equations get their name from the highest derivative that's present. In this case, it's a first derivative because it's that way it's called a first order. So we're just looking at how you name differential equations. On the other hand, you could get d squared y over dt squared is t sine t. That is a differential equation. You could get y dash or y double dashed plus y dashed plus y equals 0. That's also a differential equation. And you could get xy double dashed 3y triple dashed plus x squared equals x plus 1. That is also a differential equation. This guy will be called a second order differential equation. This one is also a second order differential equation. What would this one be called?
Third order?
Yeah. So the way you describe a differential equation, if you were talking to another scientist and you were saying, I'm working on the modeling this wing on a new kind of aircraft, right? A new type of wing for a new type of aircraft. And I've been modeling it with a third order differential equation. He already knows a little bit about what you're dealing with. Can you see he knows there's going to be a third derivative in it, at least. Now, it doesn't need to have any other derivatives, though in this case it's got a second order, or it's got a second derivative, but that's the guy that makes it third order. It doesn't matter if it's got x's or t's or any other variable, totally irrelevant. So within those, there are lots of other names. We are only going to focus, for the most part, later on, next week probably, but we'll see. Yeah, next week probably. We are only going to focus on first order differential equations. But there are two types that we're going to look at, two major types. One is called variable separable, and the other is called linear. So we're going to look at how to solve what are called variable separable differential equations and what are called linear differential equations. It's useful if you can tell people a little bit more about your differential equation. An analogy. Do you know how when you integrate things, you would do a power rule, a U substitution, or maybe an integration by parts? Wouldn't it be very helpful if someone says, I'm going to do an integration by parts integral, or I'm going to do a U sub integral? Because the minute they tell you that, don't you know how they're going to solve it? And aren't there integrals out there who can only be solved using integration by parts, right? By that I mean you can only find the integral, right? So it's very helpful if we can do that. You don't need to know this, but just out of curiosity, do you see that guy there? His full title is a second order homogeneous differential equation. Don't need to know that until you do diff-ec. But many differential equations have a name associated with them, because if you know what kind of differential equation, you already know how to solve it. Because the ones that are called variable separable, they're solved one particular way. The ones that are called linear, they're solved in a totally different way. So if you can recognize it, or you're told what kind of differential equation, it helps a lot when it comes to solving it. Well, let's look at solving a very simple one. Suppose I told you that I would like to solve this differential equation. Any thoughts about how you could actually do it? How could you use this to find out what y would be equal to? Right, you're the first person ever to see this puzzle. What are you going to do? I know the derivative of this is that. We're almost running short of time. It's much better if you just go for it and you get it, because if you do it right, if you tell me the right method, it's going to stick. If I just tell you what it is, it's not going to stick anywhere near as easily. Have a shot in the dark. What might you do to go from here to here?
Multiply both sides by the derivative of x.
Interesting. That is actually very close to solving these guys. I like your thinking. I like that thinking. All you do is integrate. Would that make sense if I know the derivative? If you want to undo a derivative, don't you just integrate things? But hold that thought that you gave me. When we come to do those ones, you're going to see a technique, virtually what you just said. Now, add 1 to the power, done. 4 gets you 4x. Of course, don't we need a big C? Because essentially that's an indefinite integral. So there's your solution. The solution to this first order differential equation is this guy. We have a name for this guy. Because he's got a plus C, and C could be +1 or +21, we call this a general solution. To the differential equation. In fact, we don't normally even call it a general solution. We call it a GS to a DE. You say it out loud as general solution to a differential equation, but you don't want to have to keep writing that lots of times. Now, suppose I gave you the same question. Here's a differential equation. And I told you that y of 0 was 7. This extra piece of information has one job. Doesn't it allow me to find out what C is? So I already know what the general solution is. It's 1/3 x cubed plus 4x add C. When they write y of 0 equals 5, what they're telling you is that when x is 0, the y is 7. That's what they're saying. So this guy is 7 when x is 0. Oh, we now know that C happens to be 7. So our solution is now a little bit more specific. And we have a name for these kind of solutions where everything is known. It's called a particular solution. To the differential equation. And of course, we abbreviate it to PS to a DE. Any questions so far? We're just getting used to the nomenclature, right? The language of differential equations, what things are called. Are you comfortable about how you name them by the highest derivative? How when you solve them, there's two kinds of solution. There's the general solution. That's the ones that have a plus C in them. And then there's a particular solution where the plus C turns into a specific number. But when you do it, you are given an extra piece of information to make that happen. And this extra piece of information is given a name. It's called a boundary condition or an initial condition. So far, so good. Almost finished with the, the intro, the jargon, the language. Let's take it just one step further. Suppose I have a second order differential equation. The variable's t instead of x, that's no biggie. And I want to solve it. Well, if I take an integral of both sides, right, if I integrate both sides, let's see what we get. Well, if you take a second derivative and integrate it, you will get a first derivative. And add 1 to the power, here we go, plus C. Now, if I integrate it again to find the function, that means I have to integrate this fella, including the c. Well, that's going to be e to the t. Add 1 to the power, you get that. Now be careful here. What will the c, the plus c, get me if I integrate it with respect to t? What will that get me?
T.
Just t, or a little bit more than just t? You're halfway there.
CT?
That's it. See, if that was 5, wouldn't you get 5t? If it was 2, wouldn't you get 2t? Isn't c just an unknown number? That's all an RPG constant means, right? It's a number, you don't know what it is, but you know it's a number, right? It's like 42. So whatever that number is, if you integrate it, won't you get ct? But of course, I'm integrating a different integral now. Doesn't that mean I have a new RPG constant? And why am I calling this one d and not c again? Why do I use a different letter of the alphabet for the next arbitrary constant that you get when you integrate? Why is it not c and then c again?
Is it because they can't take on the same value?
Yeah, they may not be the same value. You know these unknown numbers. Couldn't the first unknown number, the c, be 42? And couldn't the second one be 4, right? You don't know what those numbers are. You just know that they're numbers, right? That's an arbitrary constant, an unknown constant. Different, guys. This here, that whole thing, is the general solution to this differential equation up here. Any questions so far? Are we good? I'm just getting myself set up here, if I can. I didn't want to do that. Right, if we're good, then I shall move on and we'll talk about our first section then, which is section 9.1. And section 9.1 is basically checking solutions. What do I mean by that? You're going to be given a differential equation and you're going to be given what we believe is a solution. And you're just going to check that it does in fact work. So this is an example of question 1. You are told that this ugly fella is a solution to the differential equation y dashed plus 8y equals 8e to the x. So I want to check that this in fact does work for this differential equation. And so I guess really all I need to do is find out what y dashed is and put it in here, plus 8 of these guys. And if it works, shouldn't it equal 8e to the x? So let's see what that looks like. Here is that fella. If you find his derivative, so we're differentiating, not an awful lot happens, but are you okay with the derivative? So I'm now going to take this fella and see what we get. So the first derivative plus 8 times what y is should equal this fella if it's going to work. Right, the first derivative is 8/9 e to the x minus this guy, plus 8 times y, which is, let me check my one. Which is this guy. And if it works, it should equal that. I'm not convinced it does. Here goes. 8/9 take away this guy, plus 64/9. Something's not right. My apologies. I didn't write that down. So that's why it wasn't working. Okay. So pretend I never did that last one. Here is the original function. Its derivative. That then becomes this guy. That's better. So y dashed, 8 lots of y should equal this. Y dashed is all of this, so what's that? 8/9 e to the x. Take away that guy. Plus 8 times this guy. Should equal that guy. I have 8/9 of this guy, take away 8 of these guys, plus 64/9 of this guy, plus 8 of this guy. That kills off that. These two add together to get you 72/9. But wait a minute, isn't that 8? And go. Right, it works. So what's the advantage of this? Can you imagine that you actually do solve your own differential equation? And when you solve it, you figure out that's your answer. But wouldn't you want to, like, if you could, especially in an exam, to check it? Well, if you wanted to check it, you do it like this, right? You plug it in and see if it works. So a little hiccup, but I sort of caught it in the end. This one is like question 2. We have to check, verify as they call it, that this is a solution. So this guy here, we have to check, is this a solution to this differential equation? So I know what y is, so I should be able to find dy by dt. If you differentiate this guy, won't I have to do a product draw? So the derivative, just this piece here, is f dash j plus f of g dashed, -6 times cosine of t, plus that, so you're getting this guy, and the derivative of that is negative sine t. And I guess I could stick on this bit at the end, but let's tidy this up first. So -6 cosine t plus 6t sine t minus 6. As you differentiate that, you just get a number. So I now know that guy. So t times this guy should equal y plus 6t squared sine of t. And if it does, we've proved what we're being asked to prove. So it's going to be t times the ugly mess. Should equal y, which is this fella, plus this fella. Right, if you distribute this, you get this fella plus this fella minus this fella. And let's check it, see if it works. This guy matches him. Yeah, that works. This guy matches him. That works. This fella here matches him. It works. And in this particular question, you got an extra little bonus where it says that the initial condition that y of pi should equal 0. So when t is pi, y should be 0. Guess I should check that out then. If you take your y value, which is up here, if you plug in pi for t, do you get the answer 0? Well, let's find out. Negative 6 pi cosine of pi, take away 6 lots of pi. Anybody know what the cosine of pi is? Because it is a number, it's not 0.
-1.
So -1 times that is plus 6. Yep, it matches. So everything's cool. So if I say to you, here's a differential equation, check that this guy is the solution. Basically, this is how you would go about it. Right. Different kind of tack on the next question. And this next question is asking you, for what values of k does a particular, it's basically question 3. Y is equal to the cosine of kt. And they're saying, for what values of k does this solve this particular differential equation? So, will it work for every value of k in the universe? Will it only work when k is 1? Will it only work when k is maybe 2 or 3 numbers? Our job is to find out for what values of k is this a solution to that. Okay, so I'll start off with this fella. I'll find his first derivative. Well, if you differentiate the cosine of kt, you get negative the sine of kt. Do you get anything else when you differentiate this?
Times t.
The other letter, times
Okay.
k. T is a variable, I know it's hard to tell, but t is a variable and k is not. Now, if you want to find the second derivative, you differentiate a sine, you get a cosine of kt, right? So a negative sine gets you a negative cosine, times you get another k, so you get that. So I want to take 81 second derivatives. And it has to equal negative 16, this guy. So negative 81 k squared cosine of kt has to equal negative 16 cosine of kt. What I'm going to do next is I'm going to just divide both sides by that, essentially cancel them out. And I now have that. Where do I go next?
The square root of 16 over 81.
Okay, so what you're going to do is divide both sides, and that'll get you 16 over 81. And then you said, quite rightly, the square root of that. Shouldn't the answer be plus or minus? Because in this situation, both can happen. And that actually comes out quite nice. So plus or minus 4/9. So I guess there's two answers. There's a 4/9, right? And the other one, negative 4/9 would also work. Are we good with that question now? If we are, I shall move on. Now let's show you what the next question looks like. Oh, I get a chart or something. Oh, thank you for telling me that. Let's have a look at the next question. It's easy to, easy is the wrong word. It looks simple, that's better. Here's a differential equation. You see it up here, it's a second order. Here are candidates for the solutions. Now, this question actually involves a lot of work, because let's randomly take one. Let's check that one. Well, if I wanted to check this one, wouldn't I find its second derivative, add on this guy, and if the answer was 7 sine x, I'd use it. Now, what you might think is, well, once I find the one that works, I don't need to do anything. But that's not the case. It's quite possible. In fact, I wouldn't be at all surprised if there's two answers that work. I'm not saying it's those two because I haven't done the question. But what it really means, you have to do every single one. And I know how WebAssign works. Let's suppose that there were 3 answers, just for argument's sake, but you only found 2 of them. Won't WebAssign just say you're wrong? It won't really give you any clues like, well, you're right with 2, but there's another one you need to go looking for, right? Or you picked 3, but one of them you shouldn't have picked. So you can get really frustrated with a question like this because of the lack of help when you don't get it right. So bear in mind that every one of these guys could be a solution. Now, I'm not going to do every one of these, but I'm randomly going to ask you, because it's really a guess. I don't see how you could really tell. Which one do you want me to check to see if it might be a solution? Right, they're called 1, 2, 3, 4, 5. So pick a number.
How about number 2?
Pick that one because it's the ugliest? I would.
Yeah.
Yeah, because if I can do this one, right, or if I can check this one, won't the others probably be a little bit less work? Okay, so I'm going to have to return now to the white screen and see what's going on here. First thing, would you agree that I need to find the second derivative, right? Oops, do it now. Would you agree I need to find the second derivative? Which means I'm going to have to find the first derivative and then differentiate that. And that's probably not going to be pretty, because just looking at what's here, I think I'm going to have to do quite a lot of work at the side. So I'm going to find out what the derivative of this guy is. So it's going to be a product rule. So it's going to be f dash g plus f of t just. It's going to be 7 sine x plus 7x cosine x. So I've got 7 sine x plus 7x cosine x. Now I've got this second term. Now, it's got a negative in front of it. Do you know if I just bite the bullet and put it in here, it means I don't need to worry about plus or minus later on. I think that's less mistakes if I do that. So, of course, it's another product draw. -1 cosine x minus x times negative sine x. So what does that get me? It gets me negative cosine x plus x sine x. I wish I'd left more room. So I'm going to get negative cosine x plus x sine x. And we now have our guy. I'm doing a quick scan. Nothing, not one darn thing cancels or combines with any other thing. So straight into second derivatives. The first one gets you that guy. I'm going to do this in my head. So it's 7 cosine x minus 7x sine x. That guy is negative cosine, so you differentiate it, you get plus sine. And this guy here is going to be sine x plus x cosine x. Okay. Does anything here want to play with anything else here? Oh, I guess I could add these two together. And I could add these two together, so that's something. So I've got 14 cosine x's. Take away that guy. Plus 2 sine x. Plus that guy. Okay, that's me got everything I need. Second derivative first. So all of that. Add y underneath. So I'm just going to add 7x sine x minus an x cosine x. That's cool. And if everything works out, it should be 7 sine x. Let's see what we get when you take this second derivative and add it to this y value. Well, that cancels, that's nice, and this cancels. But after all that hard work, it doesn't fit. So it's not a solution. Are we good? I get thumbs up, I'm going for it. So the theme right now is checking that something is a solution to differential equation. We're making no attempts to solve them. We're just checking that somebody else's solution works or doesn't work. Careful with my time here. Here is a differential equation. Oops. Oh, you can still do it. This guy. Right, that's a differential equation. It's a first order. And we are being asked to check that this guy is a solution. Wow. That means I'm going to have to differentiate this ugly guy, plug it in here with an x squared, then add x times this ugly guy, and it better equal 6 because we're doing a check. So let's get the cobwebs out. What differentiation technique will I need to use to differentiate this fella?
So the quotient rule?
That's what it's called. So the entire top is going to be called F, and not there's much happening in the bottom, but the entire bottom is called G. And the quotient rule is F dash G, take away F of G dashed, all over G squared. So all of the work I'm about to do is just to find out what that Y dashed is. Well, if you differentiate the top, you get 6 over x, because log x is a derivative as this. Differentiate c, you don't get nothing. Multiplied by g, which is that guy. Take away this fella, times the derivative of the bottom, which is just 1, all over x squared. Well, they cancel and you get 6. This guy gets you 6 natural log of x, take away c, all over x squared. Okay, so that is y dashed. Now I'm going to do x squared y dashed. So x squared y dashed becomes x squared, all of this, plus x times y. Y is all of this. And we are going to check that it equals 6. Well, that cancels out and you're left with this. And this cancels out and you're left with this. And almost like magic, oops. Doesn't that plus c get killed off with that negative c? Doesn't that 6 log x get killed off with that? And isn't the only thing left is 6? And that's exactly what was left on the other side. You see, we've matched it. We have actually shown that this thing works. So any function that looks like this fella here, right? So for any c that you like, +1, +41, +1,000,000, every single one of them is a solution to this differential equation. And then they have a second part. And in the second part, this is a new thing, it says illustrate that this works by graphing, well, members of the same family of solutions on a common screen. So essentially what you're going to do, I've got my calculator here, so I'm going to do a version of that, is I'm going to go y equals, clear out n that's there, a bracket, 6 natural log of x. And I'm going to pick, whoops, where the heck am I? There, 6 natural log of x, there we go. And plus 1, all divided by x. So that's me doing one example of that. Now I'm going to do bracket, 6 natural log of x plus 3 divided by x, and I'll do just one more. 6 natural log of x minus 2, because minus 2 is like adding -2. So the c could be a negative number. And then I'm going to go to my window here. I know that the log function really has problems at 0, so I'm not going to plug in 0. I guess I should do nothing 0.1. That'll do. And I don't know, 10. I'll do. And then I'll do zoom 0. And I should see some pictures in a few seconds. Not very interesting pictures. So I'm going to go and see if I can. Oh, it's still doing it. Oh, it stopped doing it now. Right. Now that I've got those guys, I'm going to look at the y min and the y max. That is ridiculously big numbers. So let's do -10 to 4 and graph it again. There you go. Can you see that's one of the curves? There's the second one. And in a few moments, there's the third one. Now, can you imagine I did 5 or 6 other versions? What you're looking here is a family of solutions. And one of the cool things that differential equations can do is that you can model dynamic situations. So can we pretend that we did a lot more than just the ones I've got? Okay, they're not quite as accurate. Right. Can you imagine that representing the flow of current or wind or magnetic fields? That entire solution, right? Every single solution you could ever draw, wouldn't that be the equivalent of something moving in a curve-like fashion? And that's one of the big advantages of a differential equation, is it allows you to model what I'm calling dynamic situations, lots of things happening at the same time. Any questions? I think we need a couple of moments break then to give our brain a chance. Has anybody, Ben, have you got, that's interesting. Have you got a joke for us?
I don't, sorry. I'll try and think of one.
All right. I'm trying to think of one. Did I tell you the one about the Prime Minister of Scotland talking to the President? Nobody? Haven't heard that one? Okay, I'll tell you that one. So the President was on the phone talking to the Prime Minister of Scotland, and after a few minutes, the Prime Minister of Scotland went and said to the President, I've got some news for you. And he said, what is it? He says, well, I've been talking to our generals and we've decided to declare war on America. And he's kind of taken aback and he says, are you sure you want to do this? And he says, yeah, we can beat you. It's not a problem. Oh, by the way, this joke is about how arrogant Scottish people are. He says, yeah, we could beat you. Not a problem. And so he's thinking hard and saying, I'm going to have to talk these guys out of it because, you know, it's one-sided. I'm just going to have to try. So he says, have you thought about it? And the Prime Minister says, what do you mean? He says, well, our Navy has got 10 aircraft carriers and 300 cruisers and 22 submarines and all sorts of other stuff. He says, what's your Navy like? He says, well, we've got 2 fishing boats with guns on them. And he says, see, do you really want to declare war on America? And the Scottish guy just says, that's not a problem. We could still beat your Navy. And he thinks, well, what about your Air Force? He says, our Air Force has got thousands of F-14s and fighter jets and bombers and stealth bombers and tons of stuff like that. He says, what's your Air Force look like? And the Scottish Prime Minister says, well, we've got 2 helicopters with guns on them. So the President says, he says, do you want to change your mind now? Scottish guy says, not a problem. Our Air Force could beat yours, not a problem. So he's kind of desperate now, and he says, look, he says, there's 2 million people in the American Armed Forces, 2 million. Do you really want to declare war on us? And the Scottish Prime Minister thought for a minute, says, you know, I never thought about that. I'm going to have to check with my generals. And he comes back in 5 minutes and he says, the war's off. The President's kind of sigh of relief and says, what was it? Was it those 2 million people in the armed forces? He said, that was the reason. We just don't have enough room for the prisoners. I get one person who thought that, okay, I got 2 now. Is that not that? But oh, now you're all crying. The arrogance of Scottish people. As stereotypes go, we are quite arrogant. I totally admit that. Okay, anybody thought of a joke before we move on? Because we did need a little mental break and that helped me as well. Okay, so we're now going to look at differential equations and seeing if we can actually learn something about what might be a solution and what might not be a solution by just using the differential equation information. So that's a bit vague, so let me try and put some meat on that. Suppose I have a differential equation that looks like this. And you are given the graph of what might be a solution. And it looks like that. But you've to explain why this cannot be the solution. Why can this curve not be the right one? So, any suggestions about how this could never be a solution? I'll put some numbers in here that might help. 1, 1. There, okay. Why this graph cannot be a solution to this differential equation? Well, you got to be able to interpret them. So let me say how I would look at this question. Would you agree that e to the t is essentially the x-axis, would you agree that e to the t is always positive, right? E to the 10 is positive, e to the 20 is positive, it's always positive. Would you agree that y minus 1, whatever y is still positive? So does it not make this thing always positive? But what's happening here is that the curve is going downwards. And when the curve's going downwards, does it not mean that at least in this range of values, that the derivative is a negative number? So that's why that doesn't work. The second one's a little bit less obvious. It does do nice things. It's always increasing. And this point here is meant to be 1, 1. Yet this is not a solution either. Let's try and explain how I can come up with why this one doesn't work. What is going to happen when y is 1? Right? So what's this derivative going to be when y is 1? Well, when y is equal to 1, the derivative is going to be e, whatever t happens to be. Isn't the derivative going to be 0? Now, what do I know about a 0 derivative? Well, I know a 0 derivative, shouldn't it be flat, horizontal? Would you agree at this point it is not? So that's why that one was kicked out. So these are puzzle ones. So take that for what it is. That's one we've covered. That's one we've covered. I have one last question and we'll have finished this. And it's about a population model. The rate of change of a population with respect to time is 1.1, the size of the population, times 1 take away the size of the population, divided by 4,600. And they ask us question A, for what values of P is the population increasing? Well, let's turn that into a little bit more mathematical. For what values of P is the derivative positive. Isn't derivative positive means the thing's increasing? So I need to figure out what values make that positive. Okay, let's take the easy part. Can we make the assumption that P has to be bigger than 0? Because if you don't have anybody, it's a silly question. So I'm really just looking at that because I know P is bigger than 0 already, so that's positive. So here's your puzzle. What values of P make this a positive number?
Anything above 4,600?
Anything above or anything? I'm pointing
Oh,
with my finger.
below, sorry.
Okay, yeah, but you were on the right track. So there is this population model says that the population will increase provided the populations, there are at least somebody, right? And anything up to 4,600. Now that's the answer to A. So the answer to B kind of comes automatically, but it's asking when is it decreasing? Well, it's going to be decreasing if you're above that number, because won't this be a negative number? Because if P is big, 1 minus a big number is negative, and negatives mean decreasing. And then they have a thing called an equilibrium solution. And an equilibrium solution is really for what values of P is the derivative 0. Because if the rate increase is 0, essentially once the place reaches that number, it stays at that number, right? Can you imagine a very weird town? But every year 200 babies get born, and every year 200 people die. That would be a rate of increase of 0. And if that happened forever, wouldn't that town just basically stay the same size if nothing else changed? So that is the end of that group of questions. And we've now finished 9-1. And I'm going to move on eventually to a new section, 9-2. And section 9.2 is called the direction fields. And from now on, we're really only going to be dealing with first order differential equations, right? So that's the only ones that we're going to worry about, direction fields and everything else. And done. And I need to find something else, and I'm not finding it yet. Okay, gotcha. Okay. Oh, excuse me. Getting a little tired. Show you what the problem is. Suppose I have a first order differential equation that looks like that. Wouldn't it be nice if I could do a visualization, right, a picture of a differential equation? So what you do, and I'm doing this one by hand, and then we're going to show you some software that does it, is that you basically do a grid. And I'm basically going to do the smallest grid I think I can get away with. And even that has got far too many guys on it. So can you imagine at each of these key points, that's where I'm putting the dots, we are going to try and represent this fella. And when we're finished, this picture is called a direction field. Okay, so let's see how it works. If I pick a point at random, let's pick this point here, right? Its coordinates are 1, 2. Then according to this fella, the derivative at 1, 2 is 3. So can you imagine at this point, I draw a little line. Can you pretend that the slope of that line is 3? Okay, what about the one underneath it? Well, his coordinates, oh God, I'm getting tired. 1, 2 is here. So that guy's 3. Yeah, that's okay. We can do it now. Now, what about 1, 1? Well, his slope won't be quite as much. It'll be 2. What about 1, 0? Its slope would be 1. What about 1 and then -1? Well, the slope there is going to be 0. And what about here? The slope's that. And then if you go through each of them, for instance, at 0, 0, the slope's 0. At 0, 1, it's 1, and then it's 2. And here it's -1, then it's -2. This one, it's -1, then it's 0, and then it's 1, and then it's -2, and then it's -3. In this one, it's -2, -3, -4, -1, finally 0. Now, can you pretend that I drew all those little lines with slopes at 2 and 3? What you're looking at here is a direction field. It's essentially what this differential equation looks like visually. And the way I tend to look at these is I think of a river and the currents that are flowing through that river. So can you imagine, just pretend that this was a river current. If I had a boat, a little paper boat, and I put it here, wouldn't the boat go to here and then up to here and then climb like that? And if I went backwards, the boat might do something like that. This would be the path that that particular boat would do. On the other hand, if I had a different piece of paper, another boat, and let's say I put the boat there, it would go something a little bit different. So can you imagine this essentially allows me to model a dynamic situation, a current in a river. I think that's pretty cool that I can do that. Now I'm going to show you one that's already been done, because nobody wants to do these by hand, especially accurately. So I'll shrink this little darling back again. And here is a direction field. And it happens to be for this function up here. Well, that's nice that somebody did all that work. You see how much work there would be if you had to do it yourself. Now, it then goes on and says, sketch the graph of these particular solutions. So imagine I wanted 0, 0. That would be at the origin. Now, if I'm at the origin, let's see what happens. You go up here and then you curve like this. And then you go up here, curve down the way. Suppose I did 0, 1.6. 1.6 is about here. Can you see that the curve would probably be a big happy face? What about 1.4? Well, wouldn't the curve come down and then hit this fella? And then come down and hit this fella? So here are the possible sketches to what I just said. So one of those four does the job, right? One of these four would represent what I just did. And you pick the one you think, which would be that one. Now, if I go to this untouched one, equilibrium solutions, is there any place in this diagram where if you hit 0, you stay at 0? Right. And here are your choices, and they are all horizontal lines, like y equals 1.5, 0.5, and so on. Yeah, it's too big. Let's shrink this guy back. So this here is a derivative, right? A differential equation. But only one of these four pictures, one of these four guys, is represented in these four pictures. So you might say, how on earth am I going to be able to tell which one of those four pictures is the right one for that differential equation? I tend to look for zeros. Right. Would you agree that this is 0 when y is 6? You agree? When y is 6, the derivative is 0. Right. Can you see that y is 6? Every single one of them is a horizontal line, so its derivative is 0. Would you agree in this picture there isn't even a 6, so I'm not even going to look at that one. This one is a 6, so it could be that one, and this one I'm not looking. So it looks like I've narrowed it down to this one and this one. Okay, so far so good. Now what else can I tell? If the y coordinate is less than 6, won't this be a positive number? So anything that's a y coordinate of 6 is a positive number. So anything below 6 has to be pointing upwards. So let's see which one of these two match. If you take any of these points, well, they're pointing upwards here, but aren't they pointing downwards here? So that one's no good. Anything underneath 6 isn't every single guy pointing up the way. So we figured it out. That guy is him. Oh, there's some others, but I don't want to waste them for you. There's a few more. So to finish, actually, good time to finish, is I want to show you how you can draw vector fields, direction fields, without all that hassle. And now I'm going to look for it because I can't find it. So while I'm doing that, will you all say hi? And I'm going to find a piece of software that I thought I'd left on my screen, but I think in my rush in, I forgot to save it. Okay, I got it. It's not the one I was looking for, but it'll do. In this screen here, this is a direction field generator by Desmos. So you go up here, you type in, say, x add y, and there's your direction field. I don't need that little arc, but that's just for the benefit. Suppose you wanted x brackets 1 minus x. That's the direction field for that. Suppose I stick a y in. Click out of here somewhere. Click here. There's your direction field. So if I shrink back and there we go. That's about it. I could do one last little thing. I think it'll take sine. I hope it does. Is it taking sine xy? Oh, there we go. Right, there's the direction field for the sine of xy. And if I can find out which one of these is doing that guy, I can make that little arc go away so it doesn't bother me. Based on the color scheme, I think it's this one. I'm wrong. Maybe this one. There we go. That's better. So with the exception of this extra little bump, all you do in this piece of software is you type in the guy that you want. So if you were going to do that question I did earlier by just looking at the clues, so what was that one I did earlier? I don't know if you can find things. There we are. 6 minus y. That's the guy. And if you look at the pictures, the one that looks like this guy, or most looks like this guy, should be the one that we chose. Now, if you want to look for equilibrium solutions, do you see a horizontal line there? Can you see that one there? That's at 6. That's an equilibrium solution. If I do this fella, here is a diagonal. Right, do you see this guy here? If you hit that line, won't you just keep going in that straight line? It's an equilibrium. All the others kind of curve back on themselves. And I think, if you excuse me, I think we'll call that a day.